Let's get it started in here. For Calc 3 today, I want to go over another strategy that we have to show that the limit of a multivariable function exists. We're going to be going back into polar coordinates for this. We want to find the limit as x approaches 0, 0 of this function right here. Let's say that we already found the limit along a certain number of paths and are pretty confident now that this thing has a limit that exists. How are we going to prove that? We can't really use squeeze theorem directly because there's nothing really that we can compare this thing to. An easier strategy would be to convert this thing into polar coordinates. We know that x is equal to r cosine theta. We also know that y is equal to r sine theta. We get this just from trigonometry. It may look familiar from vector decomposition from physics and statics. We also know from Pythagorean's theorem that r squared is going to equal the square root of x squared plus y squared. This is the raw converted polar equation. We can simplify this down by crossing out r squared from the numerator and the denominator. We can then pull out the r as a common factor. There's something pretty interesting that we notice here. We notice that cosine theta and sine theta are bounded. Cosine theta and sine theta both can never be greater than 1 or less than negative 1. There is a finite boundary where those functions ranges exist. Since the max both of these functions can be are 1, we are going to say that this entire term is always going to be less than 2. It is probably going to be a lot less than 2 because both cosine theta and sine theta cannot be 1 at the same time. But we know that they are always going to be less than that number. Using this logic, we can deduce that the function we were given is always going to be less than 2 times the square root of x plus y squared. Finally, we know that this thing is going to be defined everywhere, and the limit is going to approach 0 as x comma y approaches 0. Therefore, we can deduce by squeeze theorem that this function also approaches 0. If we did the old way and found the limit along a bunch of different paths, we would find the same thing. Good thing to know. On to statics. Be gone, calc! Last time we covered static bodies in 2 dimensions, but now our thinking is going up a dimension. Literally, we're doing static bodies in 3 dimensions. This stuff gets twice as complex. We remember that if we have a moment about a point O, that we can split the moment up into moments along the x, y, and z direction. In static bodies of 3 dimensions, we need to take this into account. Remember how in 2-dimensional bodies we can only solve for 3 unknowns? Well, hold your horses because this is going to get hairy. In a static body in 3 dimensions, we still know that the sum of the forces in the x direction are going to be 0. We still know the forces in the y direction are going to be 0. And we can even say that we know that the forces in the z direction are going to be 0. But here's where it gets scary. The sum of the moments in the x direction need to be 0. The sum of the moments in the y direction need to be 0. And the sum of the moments in the z direction needs to be 0. Overall, this makes a system of 6 equations, which means that theoretically, we should be able to solve for 6 unknowns. Luckily, this is not going to be on the midterm next Monday, because this is a lot to take in and a lot to practice. We could solve for 3 unknowns before, but in 3 dimensions we can solve for 6. But let's table that for now, because I want to go over something that is a little bit more conceptual. There are ways that a problem can be set up that make it absolutely impossible to solve, or at least solve correctly in our current methods of statics. And by our current methods of statics, I mean the ones that have been taught to me. Let's learn those 3 situations. Let's say that we have a truss here. There are 3 forces being applied at an angle on the top. We also have a weight force that is being applied at the center of mass. In order for this thing to be in static equilibrium, we need to have some forces opposing these forces, so it all cancels out. Let's say that in order to get this thing into static equilibrium, we attempt to put it on 2 pins. One at point A and one at point B. Let's break this down to show why it is absolutely impossible to solve for the forces that A and B will be placing on this truss. The forces at the top can be broken down into X and Y components. Pretty simple. Here's where this problem falls flat. Remember that a pin can sustain a moment of force in the X and Y direction, so the reaction forces at pin A are going to be a X and a Y. Since there is another pin at point B, a reaction force in the X and Y direction can also be sustained there. How many unknowns are in this free body diagram? 4. There are 4 unknowns. But in two-dimensional static situations, we only have 3 equations. It is impossible to solve for a set of variables when you have a system of equations with less equations than you have variables. This is the first situation that we got to watch out for. To see the next situation that we have to be wary of, let us replace the pins with rollers. Remember, a roller can only sustain a reaction force that is perpendicular to the surface that the roller is on. We are going to have 2 reaction forces, one at A, one at B, acting both directly upwards. How many unknowns do we have this time? We have 2 unknowns, but we have 3 equations. This is technically mathematically plausible to solve, but unless the problem specifically tells you that this situation is in static equilibrium, you should not attempt to solve it. You have fewer unknowns than you have equations. Because if it is not specified that this situation is in static equilibrium, then this is going to be moving. Because there is nothing to oppose these X direction forces up here. So if we see this, we don't try and solve it. The third situation is similar to this one. We add a third roller in the middle that applies a reaction force directly upwards. We call it C. Now we have 3 unknowns, A, B, and C. Does that mean that we can solve for the resultant forces? We run into actually another problem that we ran into before. These reaction forces are all pointing directly upwards, which means that there is no opposition to these X direction forces up here. Meaning that even though we technically have the correct amount of unknowns, that this situation is still improperly constrained. Capiche?